Welcome everybody to day 18, week 18, day 1. And we've got a couple announcements to do and some extra credit opportunities for you guys. So we'll get through those first so that you guys can't miss them. First extra credit opportunity is Python. Oh, I can't connect to the server. Ooh, that's not good. There we go. Weird. Okay. So the first extra credit activity is to learn Python. And that'll be due at the end of the semester. So Python, introduction to Python for space exploration with NASA. And so NASA put together this really gentle introduction to Python. First teaches you about Python and then works you through installing it on your local machine. Using VS Code to write a Jupyter notebook is what it's called. If you went to Steph's data science talk on Friday, she talked about Jupyter notebooks. So this will install Jupyter notebook. You can see how those work. They're real nice, easy to use, and things like that. Learn about if statements, and then write a little function, and that's it. So it walks you through the basics of Python, variables, I guess loops, even though the way they teach loops is kind of basic. Like there's a better way of doing loops than the way they teach here. And I think they go through like a function or something like that here too. Count by calling a Python function, yeah. So for every rock in the rock list, call a function, yeah. So they go through the basics of the language. And like I told you guys, there's a typical junior level class called programming languages, and in that class, we learned a different programming language a week. Python is supposed to be one of the easiest languages to learn, so I think this is a pretty doable extra credit opportunity. Let me post that into Discord and I'll have it up on Canvas once class is over. When is the job assignment due? You haven't gotten it yet. Yeah. I called an optional on it after looking at the BST competence exams because I want you guys getting more experience with pointers, which brings me almost to the Q's assignment, not quite yet. So this is one extra credit thing. So what you're gonna do is you're just gonna do it and then you're gonna screenshot that you finished it. You have to log in, I guess. I apologize, it is a Microsoft thing, so I apologize for that. But basically when you finish everything, these things light up. And I don't know, probably take a screenshot of like your Jupyter notebook or something too, because I just had my Fresno State students submit this, and like one of them submitted a screenshot of it being done in like 45 minutes, and I'm like, I don't even think that was enough time to install the software, and so I think you just click through everything and submit, and then just claim the extra credit. So I'm gonna want to see a screenshot of you having written some code in Python. That's it. It's pretty low key, but that's another tool in your tool belt. So C++, C, you kind of pick up C along the way when you learn C++. C is just C++ with a different philosophy and less in it. No real classes. They have structs, but no classes, and everything's called by pointer instead of called by reference. You know, it's C++ with a stripped down standard library and a different philosophy where everything's explicit. There's no constructors, there's no destructors. You get to see everything that's happening, and some people prefer that. But you'll basically be able to do C programming. And C-Sci 40 was basically C. So you know C, C++. You are going to do a Java assignment, and that'll be given on Wednesday. And if you do the extra credit, you'll know Python. And those are the 4 biggest languages out there. So other than JavaScript, whose existence I refuse to acknowledge. Where is it? Number 1 language in the world, C. Second place, Python. Third place, Java. Fourth place, C++. And if you know C++ and Java, you can learn C# pretty easy. C# has some neat features. Like especially when working with databases, it's got some really neat stuff called link. It's pretty rad. So yeah, you can really pick up Java and C++, Java and C Sharp pretty quickly. They're not the same language, but you can pick them up pretty quickly. JavaScript for kids crying. Yeah, and then down here you have Visual Basic that is somehow still alive. No, I'm not going to teach that to you guys. I'm not a sadist, believe it or not. And then JavaScript is very popular in the web world. I'm not a web developer guy. I sometimes have to be, but I don't enjoy it. I have done PHP programming before to do server-side website scripting and things like that. PHP is a kind of weird ass language. You basically write code inside of hypertext. So if you have a hypertext document, then you can embed variables inside of it, and when the HTML document renders, the variable loads in that place, and so it's like you can have a code sort of running inside of the thing that's generating the web page for people, and that's kind of cool. And PHP has really nice, in my opinion, MySQL bindings. So you can go to a website and have the PHP hit up a MySQL server, grab data, display it nicely on the screen, and I've done that before. It's a weird and badly designed language, I'd say. JavaScript's a very badly designed language too, honestly. It's a dumb language, honestly. Like in just terms of like making sense. The lack of a type system is just kind of garbage. SQL's database stuff. I've done a fair bit of SQL in the past, and it's good. All of these things make you employable, right? And we'll do a little SQL in CSI 26. We will do assembly language, ARM32 assembly language in CSI 45. And assembly language, I don't know. Muya, what are your thoughts on assembly language? Right here.
It's cool, and I'll probably use it at some point, but definitely not something I want to do full time.
Yeah, and probably a full-time job in it is more of a different career path, right? Like, usually it's just a good thing to know, and you do most of your stuff in C and C++. It depends, I guess. It depends, but it is good to know. It does help you be a better computer science person. Yeah, so essentially if you guys kind of take, computer science with me, you'll know, was it like 8 out of the 10 top, or by no, I mean at least have some exposure with it. Once you have some exposure to it, once you get the basics down, then it's easy to kind of self-teach, I think. I teach everything except for Visual Basic, JavaScript, and I guess C Sharp, not really either at all. So 7 out of 10 of the top languages. And I do that for a reason. It's because I want you guys to get jobs. Yeah. Or, if you want to be an academic, guess what? There's a lot of academic stuff that takes place in Python these days, right? Not the computer science world, although, to be fair, a lot of computer science takes place in Python these days. But like, as Motzenbacher was talking about on the Friday lecture, if you are a math major, you will probably do a lot of programming. And Python and R are the two big things used in data science. And so there's a lot of sort of what you might call non-programmers that program in Python. So Python's very common, right, for that reason. Okay. So any questions about that? Basically, just run through, when you click on these things, let me just show you what it looks like. Compare values of data with Python code. And it tells you about, this is like CSI 40 level stuff, right? There's the double equals and the not equals and the less than equals. And it just shows you how to do this in Python. Print is their cout thing. So print temp is greater than or equal to 32. Temp is 50. Notice the lack of typing because it's Python. There's no types, right? So it's just a variable named temp, set equal to 50. And it's printing if temp is greater than or equal to 32. That's an expression. An expression is anything that goes within parentheses. Same thing in Python, same thing in C++. So temp greater than or equal to 32 is true, and temp less than 32 is false. You can set a variable equal to a string. Print Highland equals rock. Nope. Print basalt equals rock. Yep. So, and that's it. And you just hit continue. And so just basically, just copy and paste these things. Just kind of goof around with it a little bit. It's going to walk you through setting up your development environment. And when you do that, you get 100 XP. Get 100 XP. And as you go through the thing, it tracks what you've done. And when you're done, let's see here. Yeah, when you're done, this thing will light up. So I want a screenshot of that, and a screenshot of you having some Python and VS Code or something like that. Okay. So what are some applications of functional languages? Everything or nothing, one or the other. Functional languages kind of treat everything like a mathematical function. There's no side effects. You take an input, it gives an output. And you're not allowed to do things on the side like counting anything, which is considered a side effect. Opening a database connection, side effect, yeah. And so in order to do anything in a functional language, you have to kind of break the language a little bit. So there's some really neat features of functional languages because you can composite functions together because everything works like a function. If there's no side effects, then all these sort of algebraic operations of composition and things like that work in a functional language. And there's all sorts of kind of cool things you can do, like currying and making a new function from another function with some of the parameter values plugged in. And yeah, you can do that in C++ actually with the
Would you like one?
functional. Why do you guys keep trying to feed me candy today? This is like the third or fourth time you guys have tried to feed me candy.
No.
I don't want candy.
Really?
No, yeah, mommy's kept trying to push the candy on me. This is the second time you. No, I'm good. I'm good. Thank you though. I appreciate the offer of candy, but I'm good. Thank you. I appreciate it though. Yeah, seriously. Thank you. Okay, so there's a function type in C++ that can hold a function, and you can pass it to things like sort. So if you have a function, let's see if they have sort down here or something. Yeah, but you can have a function variable type, and it can hold a function like that, and then you can just call it. Yeah, see, so there are variables that hold functions. It's kind of cool, kind of neat stuff. And function objects. Let's see, functional header file. And there is. There you go, bind. And so if you have a variable, if you have a function named f that takes, what is it, 5 parameters, then you can bind some of those you can bind some of the parameters to hard-coded 42, hard-coded to this function, hard-coded to a value. _1 means the first parameter passed in, _2 means the second parameter passed in. And so this creates a new function called f1 that is based on f, but every time you call it, the third parameter is automatically going to be 42. The fifth parameter is automatically going to be cref. Fifth parameter is always going to be n. And then the first parameter you pass in here is passed in as the third parameter. And the second parameter passed in is passed in as the first parameter. So you make new functions out of old functions by binding the parameters to it. And there's kind of fun stuff for that, I guess. Like making the random number generator. You can use bind for that. Okay, so you guys understand? Yoxtheimer is eating candy. Yeah, nice. You guys understand the extra credit? Do this, and it will be able to. I don't know. How much extra credit do you guys want for this? I'm open to suggestions. How much extra credit do you want for learning Python? $350. 3.5 points to your individual homework grade, maybe. Same value of the last homework, 20 points. 150% of the class grade. And 350 sounds pretty good to me. 3.5 points on your individual homework. Graham's number to Zybooks. We could. Let me see what areas students need the most points in. Maybe we can let that guide the decision. Did you guys do the last SciBooks? The last SciBooks is on graphs. We're going to talk about graphs today, I promise. Let's see, sort by grades, high to low. Look at all those A's and B's in the class. You guys don't need extra credit. Oh wait, let me scroll down to the bottom. Never mind. Okay. Daily quizzes, maybe. Yeah. Pair programming, maybe. Let's go with daily quizzes. Let's go with daily quizzes. Let's have it be worth how many points have we had in daily quizzes? Kind of a lot, right? Let's add maybe 10 quiz points. Does that seem reasonable? 12. How many points would that be worth? Oh wow, that was over 10%. That's fine. Yeah, I'll make it worth 10 points on. I'll be generous. So if you guys do this, it'll be worth 10 points to your daily quizzes, and that's a pretty big jump in your daily quizzes grade. Okay, make it the only assignment. Okay, and then there is another extra credit assignment as well, and that assignment will be to make a splash screen for my videos. So you might have noticed that I've been using just sort of placeholder art for a lot of the talks that I've been giving. So here, yeah, this was just picked by Facebook, but can I not click on it? Go on YouTube. Am I gonna get copyright strike on my own video? So you notice the splash screen is just a default thing that YouTube picked. Sometimes it is, welcome everybody to the background. Sometimes, like if you look at it over here, it's just pictures of one of my various trips to France or whatever. And I would like, since I'm planning on, what the heck is going on here? So I would like to keep these videos up as sort of a resource for future students so that they can learn, the class on their own speed if they want. But in order to do so, I kind of want to have professional looking splash screens up there. So if you, for every splash screen you make, I'll give extra credit points, and I'll need to figure out exactly how many to do that. I'll probably make like a Google Sheet, and you can sign up to make one. But if you sign up to make it, please do it, because then if you don't, then there won't be one. Do you guys understand? Like, you know what I mean by splash screen? Like the image that displays here when it's the thumbnail on YouTube. So make ones for specific videos. Yeah. So I'll put up a list of all my videos, and in every class actually. So there's more than just this class if you want, and. This was kind of a fun thing I did on Friday, where we built a fully functional 2.5D client from scratch. So, in 2 hours. It's pretty good. Fortunately, Mulia was there with the trig help, right? Do you make them clickbait? I would prefer not having my face associated with clickbaity articles or things, so no like one trick the computer science majors hate, kind of stuff. There you go. Yeah, I think Muya, I think this was I think it might have been an FOV issue. Right? Like I think it might do like a fisheye.
You gotta turn on optimizer too.
The FOV.
Yeah, I think so too. Yeah, like a fisheye kind of thing. Yeah. It always curves in a really weird way.
Yeah,
looks like a fisheye.
I think I'm gonna make bindings for changing the FOV, and then I could just sit there and play with it and try and see if that undistorts the world. Okay. Learn C++ in 20 minutes. Yeah, no, please don't. Just, some nice thing like that just has these are the topics we're talking about today. And timestamps for when each section occurs, because each of these classes is an hour and a half long, and I usually talk about 2 or 3 different things in each class. And so like timestamp when each topic is brought up so that students can be like, oh, he starts talking about BSTs at 1:20, and then they can just click there. And I could feasibly put that into the comments section, or actually just comment, and then I'll approve your comment, and then people can just click on it and jump to the relevant sections without having to scroll around. So you'll do a good deed for the students of next year, and I'll have a Google sign up sheet on that, and yeah, and so give everybody a chance to take one, and then after a while take another one if nobody has taken one. Okay, and so that'll be worth some unspecified amount of extra credit as well. Okay. You put timestamps into the video now. When they scroll the time, it's found in sections. Yeah, but I don't want to have to go through them and look. I don't want to go through my own videos, man. I talk a lot. I like talking. I don't like listening. I'm a professor. Come on. They pay me to just talk. Yeah, so if you guys get the comments, then I can actually go through and either just approve them, which would be easy, or I could put them into the video itself. But I honestly don't want to skim around. So each one of you will become sort of an expert on one of the videos. And have you guys noticed, like, I actually type like fairly long essays on like some of these things that I put together for you? I don't know if you guys ever look at the...
Yeah, I looked at the descriptions. They were pretty comprehensive.
Not that one.
Except for that one.
Got something in mind. Yeah, so like I wrote a whole essay on like how you do threads and atomics and sockets and things like that. Okay. So good. And if any of them are short, like that last one I showed you, feel free to type up a little bit longer description of it. Okay, so you can see, yeah, none of these thumbnails are really very accurate. I guess this one, Motzenbacher stock. That's about it. All right, so let's get going. Putting extra credit in the last week's school. First of all, you guys have any questions about queues? So the queues assignment, you have 5 different options for how to implement a queue. I would really prefer that you guys do at least one of the queue implementations using pointers. Okay, to the point where like I might mark you down if you don't. It's like I really want to see you guys get practice with pointers. Okay, if you've already done all 3 implementations, ignore that, I guess. But I really want to see you guys. Here are the 5 things. So you can use the STL list class, you can use the STL vector class, and think about how bad a vector is at performance. You don't have to implement it well. You know what I mean? Like, you don't have to implement it in such a way that you're going to get order 1 performance. Using the vector class, why are vectors terrible at queues, by the way? Let's toss it out there. How do you implement remove with a circular array, since they rely on head and tail? You need to do an order and move. So when you remove from a circular array, you either move all the elements to the left, right one, or you move all the elements to the right, left one. And you have to be careful. You have to be very careful because it can wrap around the edge of the world, right? And so that when you're doing a circular list, the fact that your tail and the head can be on opposite sides of the world, the divider, the end of the world, makes it a little bit tricky. So there's a couple different ways of handling it. You could just do a for loop where you run until the end of the array, and then you run from the beginning of the array to the ending point. Or what I do is I just I have a .at function, and if you pass in an element past the end of the circular array, so like let's say the circular array is of size 10, and I say give me .at 15, then it goes to 5. And so if the head is, if the head is less than the tail, then I add the size of the array to the head. And then I just iterate from the tail to the head, either way. very easy. You get. Let me put that up in note. One note. Let me make sure that you guys get that, because that's actually a really important trick. You could just do 2 for loops, and that works fine too. I've seen lots of students do that. What happened here? Chat. How did you come over? Yeah. Okay. It's like, tablet is unplugged. Draw. We're back. All right, there we go. So let's say we have an array of size 10, right? N equals 10. And you're going along. You insert. 1, 2, 3, 4, 5. You pop. You insert. You pop. And you end up with something like this, where the tail is here, and the head, 9, 10, 11. Yeah, sure. So the way that I implemented it is my head, I think, is like pointing at the next place where I'm going to insert, and the tail is the next place I'm going to pop from, is the way that I did it. You don't have to do it that way. There's 4 different options on how to do it. Like the tail could be back one. It doesn't really matter. Just be consistent, and it'll work fine. So my head is the next spot I'm going to insert into. So if I wanted to, let's say, delete 9, right? If I'm going to delete 9, what needs to happen is either 8 needs to move to the right and 7 needs to move to the right, or everybody to the right has to move to the left. It's like when you delete from the middle of a vector. You can't leave a gap in. So if you delete from the middle of a vector, all the elements have to shift, let's say, 1 left. Okay? So let's say I delete 8. Okay? Then what I need to do is say, starting at this index here, starting at 0, 1, 2, 3, 4, 5, 6, 7, starting index 7, starting here, and ending here, then move all the elements 1 to the left. Okay, so 9 needs to move 1 to the left, 10 needs to move 1 to the left, 11 needs to move 1 to the left, and head needs to move 1 to the left. Okay, so do that. Start is, wherever we found the thing. So start's already set. So for int I equals start, I is less than head, I plus plus. Now, this won't work, right? Because head is at index 2, right? That's index 2. And so I is going to start at 7, so this doesn't work by default, right? Like, it'll work if head's on the proper side, but once it wraps around, it stops working, right? It's a very common problem that people have with this assignment, is they don't handle the wrapping around very well. So the approach I took is one trick that doctors hate, and that's to say, if head is less than tail, head plus equals size, something like that. And then you're like, wait, I'm going to go out of bounds. Yes, I am. So I do this rather than using square brackets, like a chump. I write a .at function. So I say, whatever data structure I'm using, r.at I. r.at I equals r.at I plus 1. And my at function that I wrote for it handles the modulusing properly. So if the variable here is past the end of the array, it moduluses it. And so if I try accessing element 15, .at will access element 5. Do you guys understand? So I just wrote it like a little helper function that would handle the modulus and the circular arrayness of it. But that's the whole thing. So this is literally the for loop. So for int equals start, I is less than head, I plus plus, array.at I equals array.at I plus 1. So it just moves everything, takes the person to the right, puts it in my spot, then moves, and it goes down the whole thing. And this part here happens first, right? Okay. So slow. So slow. Wow, it keeps scrolling. That's cool. There. That's my whole code. Okay. That's the whole thing for remove. Except for the helper function. Do you guys understand how that helper function works? Like, returns a t, it's named .at, takes a index or something, I don't know, maybe an int for the index. It handles negatives too, maybe. Int. While index is less than 0, index plus equals size. While index is over size, index minus equals size. And then return our index. Now you might be looking at this, be like, wait, shouldn't you be using modulus instead? What do you guys think? Should I use modulus here instead of minus equals? What do you think? What are the trade-offs? What's the benefit of using a while loop over modulus? Dead silence on the chat. Don't know. Good answer. First of all, does modulus work with negative numbers? Like, what I want is if the user types in give me -1, because like maybe you do this for loop the different way, like you say I minus 1 or something, you know, like you're going the other way, you're copying from the left instead of from the right. Maybe you want to do -1 and you go out of bounds to the left. So you try accessing element -1. It's possible. It can happen. It's a circular array. It's fine. If I try accessing element -1, that's the same as accessing element 9, right? So if I'm at the beginning and I go 1 to the left, I'm now at the end. If I'm at the end, I go 1 to the right, I'm now at the beginning, right? It's a circular array. So I want it to be able to handle negative numbers. And you might be like, well, why, why not just use modulus? Well, let's find out. What is -20 modulus 3? -2. Wrong. Wrong answer. Right? So modulus 3 cannot give an answer of -2. Think about it. It's the remainder function, right? So the remainder function is how many times, like if we had +20, right? How many times does 3 divide into 20? Divides in 6 times, right? 6 times with a remainder of 2, right? So that is the modulus, right? The modulus is always going to be a positive number. It's going to be a number that ranges from 0 to 2 because the number we're dividing by is 3. You can't have a negative remainder. It doesn't even make sense, right? So if we're doing -20, how many times does 3 divide into -20? negative 7 times, right? With a remainder of 1, not negative 2, 1. That's the right answer. So yeah, C++ modulus doesn't work with negative numbers. So let's see if Windows Calculator used to have that problem. I think they fixed it, right? Let's see, 20 negative modulus 3, 1. Yeah, see, they gave the right answer here. It used to give a negative number 2. Let's check on DuckDuckGo, negative 20 mod 3. Negative 20 modulus 3, remainder is 1. Yeah, okay. 20 mod 3, 1. Okay, yeah, so these are working right. C++ though gives the wrong answer. So you cannot rely upon the C++ mod operator for negative numbers, unfortunately. Right? So that, okay. But why didn't I use that? That's the reason why I did it here, right? So while the number is negative, just add the size, right? So negative 1, you add 10, you get 9, good to go. All right, because if you have an array of size 10, it starts at 0, goes to 9. If you take one step off the left, it wraps around and becomes 9. So just that's how you do a modulus, right? You just can repeatedly subtract, repeatedly add the size of the array to something to get it within 0 to 9. But you might be like, why did you not use modulus here? And the answer is I could have. For here, it would be correct. For here, it would be correct. For this part, you can't use modulus. For here, it would be correct. But why didn't I do it? Anyone want to guess? Because I'm lazy. I wanted to. Is it because I wanted to have this conversation with you about the difference between modulus and a while loop with repeated subtraction? Technically, yes. But there's a reason. There's a reason. Why? What's the difference here? Correctness-wise, they're the same. They'll give the same answer. Looks? Yeah, maybe. I mean, there's a certain amount of attractiveness to having a sort of a yin and yang aspect. You have the negatives and the positives, you know. Yeah. If there is a technical reason to prefer modulus, I'd choose modulus. But yeah, good guess. Same pattern, easy to understand. Yeah, same thing. It's readable, but that's actually not the reason. The reason is for performance. You might be like, wait, how is this more performant? Right? This is a loop, right? And so if index was like 1 billion, right, and size was 10, it would have to subtract 10 100 million times, right? That's an order n operation, right? This is garbage performance. So why am I choosing it for performance? Well, the reason for that is because I know my algorithm, because I know, in fact, I might even make this function private so that only I can call it. And I know I'm only going to be calling this with an index that is close to the right range, right? At most, probably 1 size of the array outside. Under some bizarre circumstance, maybe 2. You know, I probably could have done this with an if statement, but I want my code to be correct. And a while loop and an if statement are actually, yeah, more or less the same thing. So, in terms of like the assembly code, just the while loop jumps back up to the top, and the if statement keeps going no matter what. So if this while loop only gets called once, it's basically an if statement. It's an if statement, 1 comparison, 1 subtraction, then it moves on. A modulus, how expensive is modulus? Well, modulus depends. It depends on the system you're on, but you know, just as a preview of the kinds of things we worry about in CSI 45 and why CSI 45 is important, modulus just as a ballpark number, and this is a fairly large ballpark, is about 80 additions worth of CPU time. Okay, just as a ballpark. Some of them could be in the teens, Some of them it could be 200 to 300, depends. But just as sort of a rule of thumb, let's say it's 80. Like the amount of time it takes you to do 80 additions and subtractions, you can do one modulus. This is one subtract and one if statement. And maybe a go-to to jump back up to the top. So 3 commands, maybe? So 3 versus 80. If you get into branch prediction and branch prediction misses, maybe we could call that cost 12, something like that. Either way, it's probably going to be faster. It's almost certainly going to be faster. Could be wrong. And benchmark it, right? Find out. But that's why I would write this function this way, because if you know some things about how your code's going to get called, you can make optimizations and tweaks and things like that to make it faster for your personal use cases. If I was writing an at for just like anybody can access, element 5 million, whatever, I wouldn't do this. I'd use modulus instead. And for this, I would do a modulus also, and if the number was less than 1, add the size of the array to it to fix C++'s lack of mathematical correctness. You guys comprehend? Comprendez-vous? This would be a little helper function to get the nth element out of an index, and if you go beyond the edge, it just wraps around. If you go beyond the edge the other way, it wraps around. So, can moduli, subtract, or add the second number again and again and again. They can't do it faster like we can in our heads. Actually, the modulus, it's actually quite clever using, you use like logarithms and things like that, and bit shifting and things like that. But modulus needs to actually do a division, and division's actually expensive, right? More or less. So, I don't know, maybe they could optimize it so that if it's close, it just does a subtract or something like that. I don't know. But like I said, this is just sort of a ballpark figure. So, this code will probably be 5 times faster, something like that, in actual use. So, okay, so that would be the delete function. So for the delete function on a circular array, you just have to move. You guys understand this for loop? Just repeatedly grab the person to the right, move it over, and go to the right, grab the person to the right, move it over, and you just have to be tricky about wrapping around. The wraparound bit is that's the big brain moment right there. So I just make the head 15, and then I just iterate from, start to 15, and let the .add operator handle all the circular axes. Yeah, you guys good with that? That's a good question. You guys know CD minus, by the way? Takes you to your last directory. If you need more directory history than that, you can use push D. Push current directory onto the queue, and then you can move around a little bit, check out the different directories on disk. I always felt like a hacker man when I was checking out Etsy and really digging into the guts of the system and be like, oh, what is? I'm gonna open up the networks. Oh, I am hacker, dude. Look at this, networks. It's incredible. Okay. So I've browsed around, and then I want to go back. I can just pop D. Okay. Press again. Push D. Directory. No, sorry. There you go. So you push you push the directory you're going to move to, and that saves your current directory onto the stack. And then if we go into the hacker directory and then do pop D, then it takes us back into this. It's a stack. It's actually a stack of directories. So you can push things onto the stack. You guys know what a stack is now because of CSI 41. And then you can pop things off the stack. And if you ever want to consult the size of the stack, you can type dirs, and it shows you all the different directories that are pushed onto the stack that have been saved. So. Okay. Yeah, I don't use it very well. So you can tell. Okay, so. Alright, so for the q.h, again, there's going to be a lot of benchmarking on the server. If you wish, you can benchmark it on your home machine to save the server. Server will get bogged down the night before the things do, so make sure you copy paste it onto your local machine, run on VS Code, something like that. I think I did that with the threading thing. I actually got that to work. Where did that go? So I wanted to see if my threading thing was broken, or if it was just the server not having more than one physical core. Okay. Recent projects. Cool. Is it still loading? Is it really still loading? That was a long ass load to load a text file. Okay, so let's compile this. Let's see here. Build the solution. All right, it's up to date already. All right, cool. And then we will run it. Ready. All right, here we go. Wow, that is a tiny, tiny font. Edit. Let's see, properties. Font size 36. There we go. How many threads? I want 6 threads. How big is the array? 1,000, million, 10 million. All right, so the multi-setted, slower. Okay, let's run it again. Okay, so with multi-threaded, it looks like by the time you get up into like the 100 million range, the multi-threaded performance is better. Because remember, there's an overhead to creating a thread and having to synchronize threads and things like that. And so for smaller things, it's just not worth the overhead. But here we have 100 million, and we're beating the performance by a factor of 2. So this was the thread thing that I showed you guys earlier. Let's zoom in on it. Where we just add up all the numbers in an array. So we generate a random array, we add them all up, and we use the chrono library to compute how long it takes. And so single threaded and then multi-threaded. So for multi-threaded, I just basically create a thread for each of the different slices of the array, and then join them all, join weights until the thread's finished. And once they've all joined back together with main, then we stop the clock and print out the benchmark time. And so we did beat the single threaded performance once the array size climbed up into the probably tens of millions, somewhere in there. But for smaller things, just single threaded performance is going to be better. Okay. You guys understand? You guys remember this code here? It just takes a pointer and a start and an end index, and it just adds up everything between those two indices. You could probably use accumulate for that, actually, huh? I wonder if that'd be faster. Because this is using accumulate, isn't it? Let's try that. Let's try switching this out. So we're going to accumulate from array plus start to array plus end. Remember, pointers are iterators, iterators are pointers. They can basically be used interchangeably. Accumulate not found. Having an issue with this? No? No? Yeah? No? What's your problem? What's your problem? What's the matter? Array plus end. That's a pointer to the beginning of the range we're going to add up. That's a pointer to the end of the range we're going to add up. That is the unsigned long, which should be compatible with that. Why? And it's not telling me. It's not actually I'm hovering over it. Nothing. Okay, you know, I'm going to try building it. Build solution. If you got a problem with me, just tell me. What a high performance machine this is. It's still building, by the way. It's not done yet. Visual Studio, why are you so terrible? This is really bad. This is just basic, boring C++. There's no reason for the compilation process to take so long. It's like one page of text. It's still building. Okay, I'm gonna throw this in the background. Oh, there we go. Build started. Oh, good. It started. After, there we go. All right. Wow, that was pathetic. All right. Now we're gonna run it. How many threads? We'll do, I don't know, 5 threads again. 10 million this time. And, okay. Yeah. Still not good performance. Because like I said, there's an overhead to doing threads. So let's do 2 threads. Let's try 2 threads. 100 million. Yeah, it's about the same. So no real benefit to using. Actually, let's try one more time. Let's try the previous run that I did with, what was it, 5 threads, 100,000, 100 million. And maybe it's a little faster. Yeah. Okay. So, yeah. So using multi-threaded code, you can get more performance. And so learning how to do that is the next assignment. Okay, so for Q, yeah, pointers. Okay, so one thing I wanted to talk about in pointers today was, do I still have the tree public BST? Do I have BST code? Okay. So the delete function is always the biggest pain. So if it's on the tree, we delete it. Case 1, leaf. Case 2, deleting a node with the left child. Case 3, deleting a node with the right child. Leaf. If we haven't handled deleting the root, have we? Okay, yeah, we are handling the root. Okay. So if the last element in the tree, then it handles it. Okay. But we're not handling it here either. Yeah. Okay, so, and then, yeah, anytime you're deleting the root, you have to make sure the root pointer moves as well when you delete the root. And then the case for deleting 2 children. And this is, something else, I guess. Like I said, this is the most annoying one, because if you have a, let's go over here to OneNote, and let's talk about deleting from a binary search tree. Because the next binary search tree company's exam goes live tomorrow afternoon after Muya's review section, which is what time, Muya? 3 o'clock. Yes. So let's say we're going to delete 5. So some of these things are easy to delete. Like if you're going to delete 7, you just set 5's right pointer to null and you delete it. All right, easy. Deleting a leaf is really easy. You just have the parents. You just set the parent's pointer to be null and delete the memory. Easy. If you're deleting somebody that has 1 kid, like if we had an 8 here, then you just set the pointer to be here and delete it. Easy. Or if you had 1 pointer here, and you want to delete 7, you say 5 points to right equals 7 points to left. And so this guy's right pointer is going to point to whoever his left pointer is. And then you delete him. Bloop. And there you go. You have a perfectly valid binary search tree. Okay. RPG is not graded yet. Yeah, I kind of forgot to do that. I'll get to it. So let's put this back here. 7. So the tricky one, though, is deleting 5, or 3 in this case, because they've got 2 kids. And so if you got 2 kids, you can't just be like 10 points to 3, because then what the hell happens to 7? You know what I mean? Like you can't do that. You know, that doesn't make sense. Be on the wrong side. So how you delete a kid with 2 children is this. You find the previous, or you can find the next. I'm just going to use previous as the bench, as the standard way that I'm going to do it. Find the previous value in BST. Okay. So how do you find the previous value? What number comes before 5 in this tree? Okay. Anyone? What number numerically is before 5 in this tree? 10? 10 is numerically after 5. Talking about comparing values. Not anything to do with pointers or anything like that. Just numerically, what number is before 5? We were to print all these numbers out. Yeah, 4. Very good. So, what we do is we get a pointer to this guy. So if this is the person we're deleting, then we get a pointer to the number previous to him. And what we do is we just switch the values. And because it's the previous value, it doesn't break the tree, right? So I could have actually switched the value of 5 with either 4 or 7 without breaking the tree, because it's the number numerically in the same place, essentially. After 5's gone, 5's place can either be taken by 4 or by 7. It doesn't really matter in this case. Like I said, I'm going to choose the previous value. Okay. So what you do is you find the previous person, you take their value and put it into the data up there. You don't mess with the pointers at all. Not at all. You just take the value and put it up here, and then you do a leaf delete. So 3's right is set to null, and the value here is deallocated. So how do you do this? How do you find the previous value in a BST? How do you find that guy? Anyone know? What is the code to get from here to here? What you do is you take 1 step left, you go down 1 left pointer, and then you go all the way down to the right. Remember, if you're talking about a left kid, everybody in the left subtree is smaller than me, right? So if I'm at 5, everybody in the left subtree down here is going to be smaller than 5, right? And everybody in the right subtree is going to be bigger than 5. So if I'm speaking English, I would say, out of all the people smaller than me, find the biggest one, because going all the way down to the right is going to find the biggest element in a tree. In this case, the biggest element of this tree is 10, because start at the root and go to the right. Oh, there's nothing to the right, so it's the biggest. Right? So we are saying find the biggest element smaller than me. That's the person previous to me. The biggest element smaller than me. So you take one step left, that's everybody smaller than me. And then you head all the way down to the right until you hit null. And that is going to be the value previous to 5. Okay? Then you just take that value, put it up into here. Find the value previous in the BST. Put value in spot. And then delete the leaf. Delete the leaf. Okay. So you take 4, put it up into here, and you delete this one. And you're done. Like I said, it's kind of a pain. So let me show you code on how to do that, if you'd like. All right. One step left, then all the way to the right. It's like a Peter Pan or something. All right, so with 2 children, find a pointer to kid to the who is the biggest kid smaller than me. And their parent. So let's do this. What is our type? Node pointer. Okay. Node pointer parent 2 is equal to us. Could I reuse the parent pointer previously? Probably not. So I am going to need to handle probably all these things. I'd probably special case out into a separate if statement up top. But if we're deleting the root, handle all those separately. Okay, so we're going to start here, and we are going to start node, I don't know, temp2 is equal to current points to left. I know this is not null because we have 2 kids. So, we know this is not null, so we're going to start with a pointer. So in order to find this guy here, we are going to start with a pointer parent2. Where's my mouse? We're going to start with a pointer here, parent2 pointing at him, and temp2 pointing at him, and then we're going to iterate down this way, and the parent's just going to follow one step behind the child. So while temp2 points to right is not null, so while temp2 has kids, move to the right. Temp2 equals temp2 points to the right. And then the parent's going to follow one step behind. Parent is equal to temp2. And then this loop will break when temp2 points to right is null. Right? This will go all the way down the tree, the left subtree. This goes left one step. And then it's going to go until temp2 points to right is null. And when it stops there, then it breaks. The parent will be the parent of that node, and the temp2 pointer will be pointing at the final person in the way. So we just swap the values, of temp2 and who are we? Current. So we just switch the values in them. These are pointers. So we switch the values, and you could just copy it over, but some things can be moved but not copied, and so swapping is we'll let it work with more types. If you've like deleted a copy constructor, you could still swap it, depending on what other operations you want. Okay, so we're just going to switch the two values, and then we are going to delete temp2. Temp2 is now dead, and we're going to say parent 2 points to right equals null pointer, and we're done. Yeah. So there you go. So one of the goals of this class is to get you guys, you know, kind of comfortable with pointers and working with them, kind of thinking about them at kind of a higher level. Hopefully you guys get this. If not, Muya, if you want to go over it again on a review session tomorrow. Muya, you get it? What we're doing here. So we've got two pointers going down the tree. The parent is always pointing to the parent of the person, so it's holding the last place, then it moves down, and it goes like this down the tree. And once we hit a spot where the right pointer of the current person we're looking at is null, it breaks. And so that means this person is the absolute biggest value in the left subtree. And so if you swap the values, it doesn't break the tree. And then we simply deallocate the value of the node of the leaf there. And we can delete it easily because it's a leaf. We don't have to worry about all the crazy different cases there. It's a leaf. And so, oh, actually it could have a left kid, couldn't it? Yeah. Yeah, we'd have to handle the left kid case also. If temp2 points to left, so if it's got a left kid, then parent 2 points to right equals temp2 points to left. Otherwise, because there's a possibility that this guy here has a left kid, in which case 3 has to point to the left kid. Now it's correct for everything except for root. Can we use a threat to check to see if both sides of a tree if we have a million elements in to reduce time? Sure. Yeah, if you it's fairly common in some binary search trees to keep a count of how many people are below you. That's, you know, if you're balancing a tree, for example, and you know you've got a million people in your right subtree and 2 people in your left subtree, time to balance. You know, you're way out of whack. And so if you know how many people are in your left and your right subtrees, then you can pick the direction that is smaller. Sure, you absolutely can do that. But if you actually do both ways, then you've doubled the amount of work you're doing. If you just somehow happen to know how far away the thing is, sure, you can use it. But yeah, like Muya says, a log2 operation is pretty fast as it is. So. All right. So that is that. Time to start a new topic. One of the most useful data structures in all of computer science, honestly. That is the integer. Oh wait, no. We already did that. So, we're going to talk about graphs because it's on your Zybook, so we're going to talk about it. Okay. It's honestly incredibly useful. It's incredibly useful. For those of you that are going to take me for CSI 26 next semester, yeah, it's actually that important. And I did this last year, and it helped. I talked about graphs a little bit in CSI 41, and so when my students got into CSI 26, they did better than usual. So I'm going to do a little introduction to graphs right now. C#, yeah. I was in Prague a couple of years ago, and there was this I don't think middle school, or I think he's probably in high school now, kid who wants to be a programmer. And when I told him I'm a computer science professor, I'm like, hey, just send me questions anytime you have a question. And he has, like, so over the last 2 years I've actually maintained a correspondence with him, and he's like, yeah, I program in C#, and I just thought, I don't know, it was kind of amusing way of putting it. So rather than calling it C#, I've taken to calling it C# in honor of Sebi Himmer, whatever his name is. Maybe it's his username. Okay, so graph theory. So if I have to think about all the different data structures out there, there's a lot: linked lists, stacks, queues, binary search trees, hash tables, arrays, vectors. If I actually, like, am I being honest with you, which ones do I actually use most of the time? It's going to be a vector, just when I've got nothing better to do. If I just need to store some numbers, it goes into a vector. Like, until I'm convinced that I need to worry about some big O issue. Like, if I'm making a multiplayer game and it has a maximum of 6 players, I'm just going to put them into a vector. You know what I mean? Like, I don't need a binary search tree to optimize the speed of accessing a player when there's 6 players in a game. If I'm going to be making a multiplayer game with like 32, no, still probably not. If I'm doing an MMO with tens of thousands of players, yeah, probably. Then I'm going to build a data structure that will find a player quickly. And I'm probably not even going to use a binary search tree for that. I'm probably going to use a hash table. I use hash tables for pretty much any time I need to speed stuff up, because they're the fastest data structure. Yeah. So I use a vector when I kind of don't care. They're easy. They're like the vanilla ice cream. Boom. I use a hash table when I need speed. Rarely use linked lists. Rarely use a stack and a vector. I do. They come up, I guess. But rarely use them. Decks, sometimes if I need to push at the front, I'll switch out the vector for a deck, and it's one word switching out, and then it works faster. Cool. Mostly just hash tables and vectors. But graphs come up all the time. And so this is probably the third most common data structure that I work with. Okay? And it's not exactly... let's go through it. Okay, so what is a graph? A graph is it's not this, by the way. It's not like a bar graph. When we say graph or graph theory, we're not talking about graphing, the tidal waves or something like that. No. Not at all. This is a graph. A graph is a bunch of points connected by lines. That's it. That's the super high-tech, complicated, terminology-laden way of putting it. It's a bunch of points connected by lines. What do they represent? Anything. What does a point represent? Something. What does an edge represent? Some relationship. These points could be cities on a map, and the edges could be how far away the cities are from each other. The dots could be people in like a social... If you've ever heard of the social graph theory, social graph, social networking. This is a social network. It could be. Who knows? And so this dot here might be me, and the lines might be friends that I'm with on Facebook. So I might be friends with Muya, and Muya's friends with me, and we might have a common friend. I don't know. Who's a common friend we have? No, maybe not. Okay, so this is me. This is Muya. And Muya's got his own friend, and I got my own friend, but our mutual friends are friends with each other. And then this person is friends with, like, these people. I don't know, everyone who does CSI. Yeah, sure. And so this line could represent a friendship on Facebook, and the dots could represent users on Facebook. And you just... These things can kind of... That's why I said it's such a useful data structure to know, because it's used everywhere. Anytime you're expressing relationships between objects, they're usually held in a graph. And this doesn't tell you anything about how, like, they're actually implemented. Like, do you have pointers, or do you have a hash table? Like, how do you... No, this is an abstract data type. Remember, an abstract data type is just like there are things that you're keeping track of, and there's operations you can do on it. So, for example, an operation you could do on this graph is like, give me all the friends of this person. And it would return a list of people, you know. Give me all the friends of this person, and we'll give you these 4 people, you know. So an abstract data type is the notion that there is just some concept of a data structure that has some operations on it. You don't know how they're implemented, but you can just call the thing and it gives you the correct response, you know. So for example, a graph, you could add a new vertex, add a new edge, search for, see if a vertex exists, search to see if an edge exists. Is Muya friends with Kearney? Yes or no, true or false? Or you could do something like, give me all people connected to this person here. And that's what you can do with a graph. And a lot of things can be put into a graph, like movies and actors, right? So like the dots could be actors, and the other dots could be movies, and the edge would be this actor acted in this movie. So every other dot would be an actor, and every other one would be a movie, and you could graph it. Graph theory is very popular in Hollywood. Good Will Hunting, they came up with a graph theory problem for Matt Damon to solve. Apparently, it was a graph theory problem that had stumped the professors at MIT for years, and this janitor came by, saw the problem, and just solved it, and threw the math world into a tizzy because some unknown individual had solved this very difficult math problem. And what's funny is that this math problem is actually trivial. If you take discrete math with me, I'll give you guys 10 minutes. You can solve it yourself. It just looks cool, right? It looks like, I don't know, aliens have like come down to Earth and you're deciphering some sort of alien script or something. It's actually really trivial, though. It's based on a real life story, though, where in some college, maybe it was MIT, some student arrived late for class and saw a problem up on the whiteboard, and he thought it was homework, so he copied it down and he solved it, not knowing that it had been like one of the great unsolved problems in math or something like that. And everyone went, you know, that was kind of the basis for Good Will Hunting. Okay. So, what do these things represent? They can represent anything. Like, this is a really broad, very general branch of mathematics. Like, you can become a math major and get your doctorate in graph theory. And there are so many different niches and subspecialties and like areas of research in graph theory. My discrete math professor was a graph theoretician, I think the term of it. She was actually in the math department, I think, or like half in the math department and half in computer science, something like that. And that was her area of like, you publish papers in graph theory. It's like a whole thing. So yeah, you could use graphs to represent what states are adjacent to other states, right? So you could have one vertex for like California, and then there'd be edges connecting California to what other states? Let's throw this out, a geographical question to computer science students. There'd be edges running to what other states? There's one dot, there's one vertex for every state, all 50 states in America, and there is an edge if they are sharing a border. So how many edges are coming out of California, and what states do they connect to? Got 3 different answers so far, 2, 3, and 4, that are connected to California, that are connected directly to California, that California shares a border with. What about Hawaii? Do we share a border with Hawaii? Poor Hawaii. Every time we do graph theory, Hawaii is always the sad state that doesn't have any lines coming out of it. Alaska too, technically. You're in New Mexico right now. Nice. Okay, yeah. So California would have an edge going north to Oregon, going east northeast to Nevada, and east to Arizona, right? Although when you draw a graph, technically you can move the dots around; they don't really matter. But if you're gonna, put it onto a map of the U.S., you'd probably have a dot in the center of every state and just lines connecting them, right? And this was actually a job interview question. So my buddy worked at Microsoft for 15 years or so, and he was called upon to interview people on a regular basis, and his go-to question for interviewing people was graph theory. He gives them a graph of the United States, and he says, by moving from state to state, you can take one letter from that name in the state. What's the biggest word in the English alphabet you could spell? So, for example, if you start in California, you could pick the letter A, and then you can move to Arizona and pick the letter A, Z. Where am I going with this? R. Sure, R. And then you can go to New Mexico and pick the E and spell A-R-E, R. There you go. So, but that's not the longest word. And so given this graph, and every state has different letters available at it, you can move around the map and pick a letter from each state. What is the biggest word you can spell? And he gives you 15 minutes to solve it. And he doesn't intend for you to be able to solve it, because it's a really hard problem to solve in 15 minutes. What he wants to do is, he lets you think about it, and he lets you ask questions like, all right, can I do this? Can I go back? Can I backtrack? Can I, or do I have to touch every state? You know, like what are the rules here? You know, are you giving me the graph, or do I have to make the graph? What dictionary am I using? And so he just wants to see how you think, you know. But also it's to see if you understand graphs, because like if you don't understand graphs, you're kind of crippled as a computer science person, right? CSI 26 subjects are very common on Java interviews. Yeah, 41 and 26 are the big two. Those are the big two classes, and it's got to understand your data structures, got to understand the theory of discrete math. Those are the two biggest things they'll quiz you on. So yeah, so I've thought about it for years. Like I still don't know how I'd solve it. I've had years to think about it. Like I've got ideas, but like I'm not happy with them, you know. And he actually had a person who said, "Oh, can I get a marker?" And he goes up to the whiteboard and he writes an entire solution in 15 minutes. And I'm like, "Did you hire him?" And he's like, "Oh, hell yes, yes, we all absolutely put down hire this guy immediately." And he got hired. Yeah, he had a really elegant solution, and yeah, take discrete math, and you can maybe I'll give that as a homework assignment. Let's get a job at Microsoft. Roadmaps, yeah, okay. So, for example, here's a graph superimposed over some of the Midwest states, right? What was the hardest interview question I had to do? That's a good question. As far as technical interviews, becoming a professor was really easy. What is a reference and when do you use them? Yeah, not too hard. Or what is a pointer? Like what? Yeah, what is a pointer and when would you use one? I think, and that's the reason why I'm standing here before you today, because I was able to answer that question. In technical interviews, once I had to recognize a function pointer for what it was, and that was it. Just recognize it. Didn't have to write one. There was a couple. There were a couple interviews that I went to where they would hand you like a printout, and it had code on it, and they're like, "Explain to me what this code is doing." So I'm like, "All right, give me a minute." You know, I look at it, figure it out. Looks like it's computing the average of a vector. Okay. You know. And so I've had some of those. None of them I would say were like as hard as like a homework assignment. But the hardest was in Fortran, just because I didn't know Fortran. I told them, I'm like, I don't know Fortran. I can learn it for you guys, but I don't know Fortran, and they didn't hire me, and that's fair because I didn't know it. Have I failed me? Yeah. I applied for a job doing Fortran programming, and I didn't know Fortran, and they didn't hire me. They hired one of my good friends instead, Mark Smith, who went on to work at IBM. He's a fantastic individual. I tell these stories about that guy all day. He's amazing. But then they liked me enough. They called me back for another interview to do Java programming, and so I got a job doing professional Java programming, which I preferred much more than Fortran anyway. So it all worked out. It was great. It was fantastic. Okay. So anyway, so introduction to graph theory. So here we have the center points of all these different states, and we're trying to figure out what is the fastest route from St. Paul to Springfield. So if this is St. Paul, and this is Springfield, which way is the fastest? And just use geographical, I don't know. What do you think? Which way is faster? Just take a ruler if you have to. Which way is faster? We're in Clovis Community College, New Mexico. Don't tell the Defense Department or the Department of Energy. You know, what's the fastest route from St. Paul to Springfield? We can go St. Paul to Lansing, to Columbus, to Indianapolis, back to Lansing, back to Columbus, back to Indianapolis, back to Lansing, over to Madison, over to Des Moines, back to St. Paul. There's literally an infinite number of possible routes we can take, right? 1 to 4 to 5. Okay, yeah, I'm reasonably convinced that's the fastest. Sure. What about I don't know. None of these are going to be too hard, huh? St. Paul to Columbus. So number 1 to number 7. 1 4 1 4 1 4 1 4. 1 2 5. Yeah, I think that's a little bit further out of the way. Just like looking at a straight line, I think 1 4 5 is a little bit faster. If we're going to go 1 to 7, though, what do you guys think? 1 to 7. One, 3, 7. Yeah, I think you're right. It seems faster than going this way. It's a straight line. There's really only 2 options. There's the southern route or the northern route. Okay. Yeah, I think so. Okay, so how do you hold a graph in memory? Like, how do you actually go about doing it? That's assuming we don't have weights. Yeah, I'm just using the actual geographical distance here. There's actually 2 different ways. The first way is just a big 2D array. And so for every city we have here, we just have a number. In this case, it's just true or false. Are they connected? Right? So is St. Paul, is number 1 connected to number 4? Yes. Then on row 1, column 4, it would have a true. Is St. Paul connected to Indianapolis? No. Then row 1, column 5 is a false. Do you guys understand? So for simple adjacency matrices, it's just true or false, right? So if I wanted to do this in OneNote, we're running out of time. We'll pick it up on Wednesday, don't worry. Let's say I wanted to convert this into a data structure, right? So I've got 7 rows, and so this is like the from, like maybe the rows are from and the columns are to. Do you guys understand? Have you seen this before? 1 2 3 4 5 6 7 2 1 2 3 4 5 6 7. I guess there's gonna be a true on every. I guess you can go from Des Moines to Des Moines, I guess, right? Or you go from Madison to Madison. You know what I mean? Okay, so if we're leaving St. Paul, we've got routes going to 2, 3, and 4. So we'd say 2, 3, and 4 are true. We do not have direct routes between St. Paul and Indianapolis, St. Paul and Columbus, and St. Paul and Springfield. Right? Do you guys understand what I'm getting at here? Like there's a 1 if there's a road, there's a 0 if there's no road. St. Paul is 1, Madison is 2. Do you guys like conceptually understand this? And this stuff with state traveling a big unsolved problem in CS, it depends. If you're talking about the traveling salesman problem, it's sort of solved, kind of. Not really, kind of. So do you guys understand what we have here? So this is a 2D array. It's you just make you just be like R 7 by 7, right? Like if you're going to make this in C++, you just make a 7 by 7 array and just fill it with zeros and ones if there's a connection, if there's not a connection. 2 to 1, yes. 2 to 3, yes. 2 to 4, yes. 2 to 5, yes. 2 to 6, no. 2 to 7, no. 3 is connected to 1, 2, 6, and 7. It's not connected to 4. Oh, it is connected to 5. Look at you. Okay. It's connected to everybody except for Des Moines. Okay. 4 is connected to 1, 2, and 5. 5 is connected to 2, 3, 4, 5, 6. I think my things are lined up wrong. Oh well. 6 is connected to 3, 5, and 7. 3, 5, and 7. We got zeros for the rest here. And 7 is connected to just 3 and 6. Okay. Let's try that. Okay, and so that would be a data structure holding, you know, the graph. That's it. That's it for today. So if you wanted to add a new city, you would just grow the array by 1. Like I'd probably use a vector instead of an array, right? And just use pushback and add a new row and add a new column, and you know, kind of annoying but doable. If I wanted to add a new edge, if I say, hey, we just built a new road between, I don't know, Madison and Indianapolis, then I just go to 2, 6, sorry, row 2, column 6, change it to a 1. And if it's bidirectional, if the road goes both ways, then I would go to row 6, column 2, and set that to true. And now I've got a connection. That's it. And if you want to find out, hey, give me everybody that Madison is connected to, then I just iterate across row 2, all the columns in row 2. Be like, all right, number 2 is connected to St. Paul itself, Lansing, Des Moines, and Springfield. Yeah, just iterate across and just print everybody that's connected to. That's it. So that's where we're gonna stop for today. Doesn't seem too bad though, right? Like some of the things like traveling salesman, yeah, they are what are called NP, non-polynomial time solutions to it. But just as far as like understanding like the most basic, like I don't think it's too bad, right? Just a 2D array and set things to true if there's a connection. False if there's not. You guys with me? Is this cool? There's a lot of things you can do with this, so yeah. Make sure I understand now. Okay, we'll continue this on Wednesday, and in the meantime, just get your Q's assignment done. Start early. Start those benchmarks early. It'll be a long night tomorrow night if you're trying to do your benchmarks and everyone else's. A 1-core, not very powerful CPU. Okay. Are graphs in the standard library? No. Bridges has them. Bridges has a graph data structure. Yeah. But no, I think that would be a good thing to add though. Yeah. They're pretty easy to make on your own though, as you can see. So usually it's people just slap it together and call it a day. Yeah, I think the standard library could use a graph class and a matrix class too, probably. Yeah. So not too bad, I think, right? Yeah. All right, we'll pick this up on Wednesday. Good luck with your homework and enjoy your last week of school. Peace out, guys.